Hello there and welcome to topic 7. This topic is called multivariable derivatives, and our goal is to apply many of the ideas that we've been developing over the last 3 or 4 topics about calculus and derivatives and apply them to 3 or more dimensions. So up until now we've been in 2 dimensions in the XY system, and today we'll move to 3 or more dimensions. So let's go ahead and get started with our objectives. So in this topic we have 2 main objectives. The first one is to be able to evaluate multivariable functions. So in other words, if we have a function that has many variables involved, how do we evaluate or find the value of that function at particular points? So we'll look at different examples such as like profit functions that have multiple variables. We also have joint cost functions that have multiple variables, and then production functions, which is something relatively new. Our second main objective is to talk about what we call partial derivatives, and this is how we take derivatives when we have more than one independent variable. So up until now we've had one independent variable. It's usually x or whatever is on the horizontal axis. In this topic we have more than one independent variable, so we will have more than one partial derivatives. So we'll first talk about how to find those derivatives symbolically. So we'll talk about rules, how do you find derivatives, and then we'll talk about how to evaluate them, or how to find the value of a derivative given specific points. So before we get too far into this, I just want to make a couple of notes. And that is that the ideas that we've been talking about in calculus for 2-dimensional systems, XY systems, will now just scale up in 3 dimensions. So in 2 dimensions we talked about slope of a tangent line. That's going to scale up, and we'll talk about slopes of tangent lines in 3 or more dimensions, typically 3 dimensions. So there's really nothing new. We're still talking about computing the rate of change using the slope of a tangent line. The advantage to this is that many of these functions are much more useful in the real world. You can model very complex situations when you have multiple variables much more easily than you can if you just have 2 variables to work with. So you'll see here below 3 examples of functions f, p, and capital F. So little f is just sort of a generic function that looks like a polynomial. Capital P depends on the variables L and K. That's what we call a production function. So we'll see that more later. And then capital F is called a Lagrange function, named after a mathematician, Lagrange. I believe it's spelled L-A-G-R-A-N-G-E. This Lagrange function is something that we'll use in the next topic, topic 8, to maximize functions that have multiple variables. So you'll notice a couple things about the functions. Inside the parentheses, each one has variables listed. So little f has x and y inside the parentheses, and so that's telling us that the function f depends on 2 independent variables. The inputs, the numbers that we plug in, are x and y, and then the result that comes out is f of xy. Sometimes we call that z. So z is the 3rd variable, and so z is equal to f of xy. And the capital P function depends on capital L and capital K. Those are the 2 independent variables there. The dependent variable would be p of lk, and in this case it's given a name. It's capital P. It's for production. And then the 3rd function, the Lagrange function, actually has 3 independent variables, capital L, capital K, and the Greek variable lambda. That symbol there is lambda. So that has 3 independent variables, and then a 4th variable is the dependent variable. So this is a function in 4 dimensions. But it makes perfect sense when you have multiple variables that determine what's going on, then you need a multivariable function. Notice that lambda here appears in the function just before the parentheses, and so it's a multiplier. So we call this actually the Lagrange multiplier. So that's a quick introduction to what these things might look like. We can evaluate multivariable functions in almost exactly the same way you would evaluate any function that you've seen so far. So for example, let's say we had a function like this. F of xy is equal to 2x plus 3y. Now keep in mind there's actually three variables at play here. X and y are independent, they're the inputs, and z is dependent, it's the output. So z depends on x and y. So let's say we wanted to compute the value of f of 3, 4. The way you would do this is that you would substitute 3 for x and 4 for y in the function's equation, as you can see here. So we just have 2 times 3 plus 3 times 4. And then after that, you do the basic arithmetic. When you do that, you get 6 plus 12, or 18. So the value of this function at 3, 4 is 18. And this produces what we call an ordered pair, or a triplet, where x, y, and z go together. So the order is always consistent. X and y come first, and then the dependent variable z comes last. So we get this point 3, 4, 18. Now, this is a point in a three-dimensional space. X is 3, y is 4, z is 18, and z is the height off of the ground. So you can sort of think of a room of 3 dimensions, the length, the width, and the height, and the height is the z value. The floor is the original xy plane that we've seen before. So let's take a look at what this might look like in visual form. So this is what a three-dimensional system looks like. Let's explore what different components this has. Notice that we have 3 axes. The first one is our x-axis, which you can see here. The next one is the y-axis, which is perpendicular to the x-axis. So the x and y-axis create a 90-degree angle when they meet each other. And then you have the third axis, z, which is up here. You also have what's called the origin. Instead of 0, 0 being the origin, you have the point 0, 0, 0. So x is 0, y is 0, and z is 0. That point is right there at the corner. So you can think of this sort of like a room. The corner of the room is the origin. The floor of the room is the xy plane, and then you have the z-axis, which measures your vertical distance. So if we wanted to look at where 3, 4, 18 is located, we would first start at the origin, and we would move 3 units in the x direction like this. That would leave me on the x-axis 3 units out from the origin. Then I move 4 units in the y direction like this. Now again, because x and y are perpendicular to each other, I have made a 90-degree turn at that point where I was on the x-axis, and now I move out into the middle of the xy plane, and I'm at the coordinate 3, 4 right now. Then the last component is the z-axis, or the z-coordinate, and that's 18. And so I'm going to go up 18 units on the z-axis. It looks like this. So the three-dimensional perspective here may not be perfectly clear, but if you take that distance and throw it over onto the z-axis like this, you see those two distances are exactly the same. So you're basically traveling 18 units up along the z-axis, but you're doing it from the point 3, 4 in that xy plane. And so that point right there is the point 3, 4, 18. Let's take a look at a couple of simple examples of multivariable graphs. The first one here is c of xy. C doesn't really mean much here. It could mean a cost function where x and y are two different products that you're producing and you're trying to find the total cost of production for those two items. But this function is relatively simple. It's just 10x plus 15y. And you notice that the highest power on either x or y is 1. So there's no powers like 2 or 3 here. to make things more complicated. And when you have this kind of function like this is sort of like a linear function. So this looks a lot like a line in 2 dimensions. In 3 dimensions we call it a plane. So this is a flat surface. You see part of the surface here, but because you're not seeing the entire infinite region of the 3-dimensional space here, you're only seeing one particular piece of the surface. So it's really a flat plane that goes on forever, and then you're seeing one small piece of it. Here's another example that's slightly more complicated. Notice that the powers now go from 1 to 2, so it's relatively simple. Z is equal to x squared plus y squared. And then you get what's called a paraboloid. This looks like a bowl, looks like a parabola actually in 3 dimensions, which is exactly what it is. So this reminds us a lot of y is equal to x squared in 2 dimensions, where we had a parabola that either opened up or down, and here in 3 dimensions you would have what we call a paraboloid, either opening up or down, in this case opening up. So this is another simple example of another multivariable function, and those 2 first examples are probably the easiest ones that we can sort of imagine. After that, they get pretty complicated, as you'll see here on the next slide. For the next example, all we do is change the previous equation from x squared plus y squared to x squared minus x squared. And what we get here is what we call a saddle point. That saddle point is the point where you would imagine sitting here if this really was a saddle that you'd put onto a horse. This particular function has properties very similar to a function that we saw when we were looking at 2-dimensional calculus. It has properties very similar to y equals x to the 3 in 2 dimensions. Now, the graph of y equals x to the 3 looks like this. So you'll remember that when we explored this when looking at maximums and minimums, we said that the point 0, 0 here was a critical point of this function, but it was not a maximum and it wasn't a minimum. We called this an inflection point. So this point, as you approach it from the left, it appears that point is headed towards a maximum point, but if you approach that point from the right, it looks like that point is actually a minimum point. But in reality, it's neither. It's just a single point on the graph where the function is leveling out. This 3-dimensional version of that function is what we call a saddle point. So in order to actually illustrate what I mean, we have to go to a video so I can use the software to show you what this function looks like and how it behaves in 3 dimensions. Please watch the video on the saddle point, and when you're done, come back here and restart the presentation by clicking the play button.